Welcome to this 8th lecture. So in continuation with what I was saying in the last lecture, the whole study of Riemann surfaces reduces to studying Mobius transformations, okay, and the device we use is or the the concepts that we use are basically concepts of the covering space, okay. So covering space theory, which is intimately connected with the notion of a fundamental group, okay. So I will first begin by quickly trying to recall what the fundamental group is, okay, give you an idea of what the fundamental group is, and then I will tell you the basic classification of surfaces that you can more or less easily arrive at, okay. So let me first give you a brief idea of the fundamental group. So I start with X, a topological space, of course, you know, to define the fundamental group X could have been any topological space, but please remember that at least for all practical purposes in this course, the topological spaces that we are going to consider are going to be certainly Hausdorff, okay. So so I take a topological space and I fix a point X, okay, and I am going to define the first fundamental group of X based at the point X, and it is denoted pi1 capital X comma small x, and to define this basically one needs to go back and understand the notion of homotopy, okay. So let me define what homotopy is. So it is a concept in topology which tells you when two maps between a pair of spaces can be continuously deformed from one to the other, okay. So so let me define homotopy of maps. So continuous maps F and G from a topological space X into a topological space Y are said to be homotopic, are said to be homotopic, written F homotopic to G, okay, if we can find a map, we can find a continuous map capital F from X cross I to Y, where I is the unit interval on the real line, okay. So it is a continuous map. So we write a point here as x comma t, and of course it is mapped to the point f of x comma t of y, okay, such that f of x comma 0 gives you the first map f for all x and f of x comma 1 gives you the second map for all x in x. And so this definition actually tells you that f is homotopic to G, and you can guess that this is going to be an equivalence relation eventually. So this will also tell you, or you can deduce very easily, that this will also give you that G is homotopic to f. Okay, but the point is that what we have is a continuous map which is to be thought of as follows. You think of t as time, okay, and you think of t as time varying from 0 to, let us say, 1 unit of time, if you want to say 1 second. So as time varies from 0 to 1, okay, for each fixed time, f of x comma t will give you a map from x to y. Okay, so what you are actually getting is a family of maps from x to y if you freeze, if you think of t as a time parameter varying on the interval. Okay, so let me write that down. So you know, f is essentially the collection, let me write as f sub t from x to y, where t is 0, is the time parameter, and ft and f sub t of x is just f of x comma t. Okay, and what the definition says is that f sub 0 is small f, and it says f sub 1 is small g. Okay, so f then capital F sub 0 is small f, capital F sub 1 is small g. Okay, so what is happening is that you have a family of maps, okay, and the family of maps starts with, at time t equal to 0 it is equal to the map small f, at time t equal to 1 it is a map, it becomes the map g, and then in between every other map ft is also a continuous map, and the way the ft varies with respect to t is also continuous. That is the whole point of saying that capital F is continuous. Okay, so in some sense what it means is that the map f in time is being deformed into the map t, into the map g as time varies. Okay, and actually it's a little bit of an exercise that one has to do, and then one can check that this is an equivalence relation. Okay, you can check that this is an equivalence relation, and can check, so can check it's an equivalence relation. Namely, you can check that it is reflexive, symmetric, and it is transitive. Okay, so now we adapt this this to the situation when the maps are actually maps from I itself. Okay, and maps from I are going to be continuous images of the closed interval 0 1, and they will be of course paths. Okay, so from as a special case of homotopy of maps, you are going to get homotopy of paths in a topological space. Okay, so that is what I am going to go to next. So let me do that. A path or an arc in X. Okay, so X is a topological space. A path or an arc in X is a continuous map. gamma from I to x. Okay, so so basically you picture it like this. So here is a real line that is this closed interval 0 1 which is I, and you have this map gamma and its image is going to for you so this is my topological space X, and this image is going to trace out a continuous curve, if you want, a continuous path or a continuous arc on the topological space, and you know this is going to be gamma of 0, which is called the initial point. This is called the initial point, and of course this point is going to be gamma of 1. It's going to be called the terminal point, and at any instant of time, let's say t, the path is the point that you get here is gamma of t. So as t varies from 0 to 1, the map gamma traces the curve, the image gives you the curve. Okay, so so we often also talk of geometrically this curve as the path, okay, where this is actually just a directed you know, think of it as a directed or a directed curve on the topological space, but of course you know the topological space by itself is very abstract, so you don't know whether you know it really looks like a some subset of Rn, so that you can really think of something like this, but nevertheless one imagines it like that. Okay, so we often call we often you know abuse language by saying that this is a path, and sometimes we also say the path is also a map. Okay, this is just abuse of language. Okay, now of course if you have two paths which are you know if you have two paths, then you can of course define homotopy between these two paths. Okay, so what one can do is you can define when two paths are homotopic. So let me do that. Two paths gamma, let me call them as gamma 1 and gamma 2 are fixed endpoint for short FEP homotopic if they are homotopic by a homotopy F so I must say here that this continuous map capital F is called the homotopy. Okay, is called is the homotopy that gives you this relation of F being homotopic to G. Okay, so so let me add here called a homotopy. Okay, so if they are homotopic by homotopy F such that you know F so you know the endpoints have to be fixed, so it means that always F of 0 comma t is always the same point is the same point which is the initial point of both of the paths gamma 1 of 0 and should also be gamma 2 0, and F of 1 comma t. Okay, so I should be careful about my about the way I write it. So this is going to be my space here, and I want the time variable going on the second I want it to be going on the second coordinate, so which means no matter what the second coordinate is my intermediate path should always have initial point and final point the same. So this is right. So let me rewrite it properly. Gamma 1 of 1 is equal to gamma 2 of 1. Okay. So what I mean here is capital F is mapped from I cross I into X. Okay. So this X has been replaced with Y and this Y has been replaced with X. I am sorry for the sorry if it causes any confusion, but let me again write it here. So this is let me write this as again as x comma t going to f of x comma t, and of course f sub 0 has to be gamma, alright, gamma 1, and f sub 1 has to be gamma 2. Okay, that is saying that the two paths are homotopic, but of course I want also that the end path, the the end points of each intermediate path also to be the same as any of any of gamma 1 or gamma 2, and that is given by the condition, by these two conditions. F of 0 comma t is always gamma is the point gamma 1 of 0 is equal to gamma 2 of 0, and f of 1 comma t is gamma 1 of 1 to gamma 2 of 1. So in effect what is happening is the following diagram here that helps a lot to visualize. So this is this is just I cross I. Okay, so here I have here I have x along this axis, and I have t along this axis, alright, and this is just in the R2 plane, this is just the unit square which gives you I cross I. Okay, and and then you have the topological space here x, and what happens is that if you freeze a certain time t, then you get so this is the second coordinate, this is the first coordinate. Okay, so if I freeze the time t, then if you vary x, you get this you get this line, and on this so at time t you get the path f sub t. Okay, so at time t equal to 0, so this edge will correspond to the path f0, which is gamma 1. Okay, and this edge that will correspond to t equal to 1 will correspond to f1, which will be gamma 2. Okay, and along this segment what is happening is x is 0, okay, but t is varying, so what you will get is f of 0 comma t, and that means that f of 0 comma t should be the initial it should be the initial point for both of the paths. Okay, and so this edge is mapped to one point, and then this edge which corresponds to x equal to 1. So when x is 1 you get f of 1 comma t as t varies, and that is mapped to the terminal point. So finally this whole diagram will look like this. So I will have gamma 1, I will have gamma 2 here. Gamma 1 is the map at f0 time 0, gamma 2 is the map at time 1, and at an intermediate point of time the map is going to be f sub t, and this point is going to be well, if I call this as x0, this is going to be the point x0, and if I call this point as x1, this is going to be the point x1. So this whole line segment is going to be mapped to this point, this whole line segment is going to be mapped to that point. Okay, and every this line segment is going to be essentially gamma 1, this line segment is gamma 2, and then if you take anything in between, that is going to give you the path f sub t. okay. So this is again a homotopy of gamma 1 with gamma 2 by a continuous family of maps parametrized by the time parameter, okay. And of course the endpoints have been fixed, and in fact the way I got this diagram, you can think about it that if I didn't fix the endpoints, what I will get is something that looks like a twisted type of image of the square, okay. So you would have got if I hadn't put this condition, so let me call this condition as say star. If I hadn't put without the condition star, the image would look like something like the following. You would have got so this would be gamma 1, and this will be the initial point, this will be the final point, and then gamma gamma 2 would be something else, okay, and the intermediate paths would have gone on to be like this, okay. So it would have looked like this, but then the fixed endpoint condition is that all of this collapses to a point, all of that collapses to a point, and you get a diagram like this, okay. So these are all diagrams which help you to fix ideas and to visualize, okay. Okay, so now you know what homotopy of two paths is. Then what we do next is we try to what we want to do is somehow we want to capture the idea that suppose you are, for example, on a surface, and suppose as a hole, okay, for example something like an annulus or a punctured plane or a punctured disc, okay. If I have a loop surrounding that, okay, I cannot continuously collapse it to a point, because at some point there is a hole and I cannot move the loop across the hole, okay. Therefore I will have to study homotopies of loops. And how do you interpret a loop? You interpret a loop as a path starting from a given point and coming back to the same point, okay. So and then one would like to make a group out of these things, so you will have to combine loops to form newer loops, okay, and in general that would mean that you should be able to combine paths and form new paths, and this thing is called concatenation of paths, and this is the way it's done in a very obvious way. So let me do that, let me write that down here, concatenation of paths. So suppose alpha is a path from in X, and beta is another path in X, okay, are paths such that the endpoint of alpha is the initial point of beta, okay. So the situation is as follows: you have X here, you have a path alpha which starts, let us say, at x0 and ends at x1, okay, and then you have a path beta, let us say, which starts at x1 and ends at x2, okay. So the endpoint of alpha, which is alpha of 1, is the same as the initial point of beta, which is beta of 0, and that is x1 in this diagram. There is an obvious way of combining these two paths, namely take the path gotten by first going along alpha and then going along beta, okay, that is obvious. So if you want to really write it down as a path, the only thing is that you have to scale the time parameter, because the way I have written it, alpha is supposed to go from here to here in unit time, and beta is supposed to go from here to there in unit time. If I compose it and I want a path again to go in unit time, I should do it faster. So what I do is I define the path alpha beta, okay, the path from I to x by going from x0 to x1 at double the speed if you want, at double the speed, or that is the same as in half the time, okay, and then go from and of course go from x0 to x1 via alpha, okay, at double the speed, okay, and then from x1 to x2 via beta again in half the time, or if you want double the speed, okay. So how does one can write down equations for this? It is very simple. So alpha beta is the map from I to x. It is defined like this: for time varying from 0 to half, I want the whole of alpha to be covered. So what I do is I will send it to alpha of 2t. If I do this at t equal to 0, I will get alpha of 0, and at t equal to half I will get alpha of 1. So in half the time, which you can think of as twice the speed, you have gone halfway by alpha, and then you send t to beta of 2t minus 1 for t varying from half to 1. Probably I should write 1 minus 2t. I should write 1 minus 2t. 1 minus 2t. Okay, you can see that it's obviously scaled so that when t is half, I get beta of 0, and when t is 1, no, that was right, wasn't it? 2t minus 1 was right. Yeah, 2t minus 1 was right. When t is half, it is 0. When t is 1, it is beta of 1. Okay. So, and the point is that you can check that this is a continuous function, because the only problem is you will have to check continuity at half, but at half the values match. That is because alpha of 1 is beta of 0. So this is the way you multiply two paths, you compose two paths, and then you can check that this concatenation of paths behaves well under homotopy, okay. So can check the following, that if alpha is homotopic to alpha 1 and beta is homotopic to beta 1, then alpha beta is homotopic to alpha 1 beta 1, okay. So the moral of the story is that the concatenation of paths respects homotopy classes, okay, and further so as I told you, we want to look at loops, okay. So we put the condition that you have paths starting from a fixed point and ending at the same fixed point. So what you do is that you define pi 1 of x comma x, so to be the homotopy equivalence classes of paths starting from and ending at x, okay. So it is a set of homotopy equivalence classes of paths starting from and ending at the point x. So essentially these are loops starting at x and ending at x, alright. So and then this fact that homotopy respects I mean the concatenation of paths, the multiplication of paths respects homotopy, tells you that this gives you a binary operation on this set. So the point is that makes the set into a group, and and that is called the fundamental group of X based at the point small x. So let me write that down. So we get a binary operation pi 1 x comma x cross pi 1 of x comma x to pi 1 of x comma x, which is well alpha equivalence class comma beta equivalence class going to the equivalence class of alpha beta. Okay, that this is so here when I put the square bracket I mean the equivalence homotopy equivalence class of the path alpha, and this is the homotopy equivalence class of the path beta, and this is the concatenation. Okay, that you get a well defined map like this itself depends on this fact that your concatenation respects homotopy. Okay, so the point is that for under this operation pi 1 x comma capital X comma small x becomes a group. So what are the other things that you will have to verify? You will have to verify that this operation is associative. Okay, then you will have to verify that there is an identity element for this operation, and that is very easy to see. The identity element is just the constant path. See, because I am looking at path starting at x and ending at x, I can simply look at a path which is always at x, that is a degenerate path. Okay, you map the whole interval to the point x, that is a path by definition, because it's a constant map is always continuous, so that's by definition a path. It's called the constant path at x. Okay, and that path simply doesn't do anything, it just stands there. Okay, it stays put, and obviously if you concatenate with any path, okay, you are going to get back the path you concatenated it with. Okay, so it's going to act as an identity element, and therefore the constant path will act as an identity element, and then associativity is something of an exercise that you can try. Okay, it's not so difficult, but the point is, why do you get inverses? It's very simple. If you give me a path starting at x and ending at x, the inverse path is just traversing the same path but in the reverse direction. So essentially in the equation of the path you replace t by 1 minus t. Okay, so that you are see, if I replace if in a map like this for example, if in a map like this gamma of t, if I take gamma of 1 minus t, then you can see that I am going to get the path in the reverse direction. So the moral of the story is that that provides replacing t by 1 minus t automatically provides you with a path which is the inverse to the given path, because if you concatenate it you will get you can see that it's going to be the trivial path. Okay, and it's going to be homotopic to the constant path. Okay, so basically the argument is that I'm saying take a path or in this case I can even say it in terms of loops. So take a loop, okay, and then its inverse will be going the other way, and then I'm saying this followed by this can be deformed to the constant path, and the way I do it is just by by just pulling this loop out at time t so that I just come back to 0. Okay, so it's very easy to see that you can easily see that there is an inverse element. Okay, and maybe it requires some writing down. All right, so you get an inverse element for each path, and then this becomes a group. So let me write that here. Pi 1 of x capital X comma small x is a group. Okay, this becomes a group, and okay, so this becomes a group, and this is called the fundamental group of the topological space capital X based at the point small x, alright. Now why is it helpful? It is helpful because it helps you, for example, to distinguish between topological spaces. For example, first of all you should notice that this group, for it to be meaningful, one has to be kind of not so dependent on the point x, okay, and that can be easily achieved by putting an extra condition on the topological space, that is making x arcwise connected. So so the point is that if capital X is arcwise connected, then pi 1 of capital X comma small x is isomorphic to pi 1 of capital X comma small, let me say x prime, for any 2 points x and x prime in X, okay. So by putting this arcwise connectedness you can show that the fundamental group is the same up to isomorphism, and this is achieved in a very simple way. If you take an element of pictorially, you know, so this is my topological space, and you know, this is the point small x, this is the point x prime, and if I take an element here, this is a loop based at x, so I am going to get something like this, okay, and it is going to be represented by alpha. The equivalence class will say, let me write it as square bracket alpha, and how do I get an isomorphism from here to there? What I do is that since x is arcwise connected, any two of its points can be joined by an arc, so I join this by an arc, and let me call that arc as gamma, okay. That is the definition of arcwise connectedness. So I can get a path from x to x prime, so choose one such path, and then what you do is that you first go by gamma inverse, okay, which is just the reverse of the path gamma, and then you go by x, and then you follow it by gamma, and this in principle gives you a loop based at x prime, okay. So mind you, when I say a loop, you should also understand that if I go from the point to a certain by a path and come back by the same path, that also qualifies to be called a loop, because my only condition is that my starting point should be the same as the ending point, and that is the reason why if I have a path like this, a loop like this, its inverse is this way, and because the combination, okay, I can pull out this end and shorten it to paths, smaller paths going back and forth, and then finally I can shorten it to get the constant part at the point, okay. So so what happens is that the isomorphism in this case is given by pi 1 x comma x to pi 1 x comma x prime is given by, so this is let us call it gamma hash. This just takes any alpha to, well, first apply gamma inverse, then apply gamma inverse followed by alpha followed by gamma, and the equivalence class of that, okay. So when I write something like this, mind you, I am not thinking of gamma as a map, okay. So this should not be confused with composition of maps. So when I write something like this, I mean first go by gamma inverse, okay, then go by alpha, and then go by gamma, okay. So don't confuse it with composition of maps, right. And you can check that this is an isomorphism of groups, okay. The constant path will go to the constant path. In fact, if I take the constant path here, it will go to gamma inverse gamma, and gamma inverse gamma is again homotopic to the constant path at x prime, okay. So you can check this is a group a homomorphism, you can check it is an isomorphism, because there is an obvious way to define an inverse, okay. By using the path gamma inverse, I can send any loop here to a loop there in the same way, so, and that will be an inverse to this map, and it's a group isomorphism, okay. And the moral of the story now is that if X is arcwise connected, I do not care which point I fix, the fundamental group up to isomorphism is the same. Okay, so we normally work with arcwise connected spaces and do not care about the point. Okay, so well now why is the fundamental group so important? As I told you, it is important because it helps you to distinguish between topological spaces, and that is because it is what is called a topological invariant. Okay, so pi1 of x comma x, so let me simply write pi1 of x. So pi1 of x is a topological invariant. What does this mean? It means that if you change the topological space by a homeomorphism, then the fundamental group, first fundamental group, will change only up to isomorphism. Okay, so in particular, if two topological spaces are homeomorphic, their fundamental groups have to be isomorphic. Of course, I am assuming they are all arcwise connected, so I am not worried about the base point. Okay, so if two topological spaces are homeomorphic, their fundamental groups are isomorphic. So if I want to decide that two topological spaces are not homeomorphic, all I have to do is to show that they have different fundamental groups. So for example, if you want to show that let us say the torus is not homeomorphic to the sphere, okay, the easiest way is to say that the fundamental group of the sphere is trivial, is a trivial group, okay, whereas the fundamental group of the torus is non-trivial, and saying the fundamental group is non-trivial is the same as trying to find loops that cannot be continuously shrunk to a point. And on the torus, of course, I have two types of loops which cannot be shrunk to a point. Okay, so that argument will tell you immediately that the torus and the sphere, the real 2 sphere and the torus, they are not homeomorphic. So that is the advantage of having the fundamental group. Okay, and this is a key ingredient in the theory of covering spaces. Okay, so let me write down some simple cases. So pi1 of any simply connected space is 0. Okay, so when I write this, of course I am assuming that it is a topological space which is arcwise connected, and by simply connected I mean that every loop can be continuously shrunk to a point. Okay, and if I can shrink a loop continuously to a point, it means that I can deform that loop to the constant map at that point, which is the identity element. So you are saying that every element is the equivalence class of every element is the same as the equivalence class of the identity element, and therefore if you take equivalence classes, there is only one equivalence class, so the group reduces to 0. Okay, namely of course I write 0 or maybe if I want to be, it is written 0, but maybe if you want I should write 1. Okay, so usually you use 0 if the group is additive, but and then you use additive notation only if the group is abelian. Okay, but fundamental groups can be highly non-abelian. Okay, and but in many books you will see pi1 0. Okay, so in particular, for example, the first fundamental group of say the sphere is going to be 0. First fundamental group of the complex plane is going to be 0. Okay, the same thing will happen to any space that can be contracted to a point. Okay, any contractible space is a space that can be continuously contracted to a point. So it will happen to this, it will happen to this, it will happen to the say unit disk, a half plane, but of course it won't happen to an annulus or a cylinder. So what happens is that if you take pi 1 of annulus, or if you take punctured plane, or if you take punctured disk, all of these will have pi 1 isomorphic to C, okay, and of course in a sense the punctured plane is also an annulus with inner radius z tending to 0 and the inner radius 0 and outer radius infinity in a certain sense, and if you keep the inner radius 0 and fix the outer radius, you are going to get a punctured disk, okay. So all of these and this is also the same as pi 1 of S1, which is unit circle, the set of unimodular complex numbers, okay, that's also going to be Z, okay, and you can see that pi 1 of course this is also the same as pi 1 of a cylinder, that's also going to be Z, okay. Then you can see that if you take a torus, pi 1 will be Z cross Z or Z directs from C. So let me write that down, pi 1, so here let me also write pi 1 of delta is 0, so here R 0, okay, pi 1 where delta is of course the unit disk, pi 1 of the upper half plane, this is upper half plane which is biholomorphic to the unit disk by any suitable Mobius transformation, that is also 0, and pi 1 of the torus is going to be isomorphic to Z cross Z, which is written as Z directs from C, okay. So essentially what is happening is that if you take the torus, you can the fundamental group is Z cross Z, which means that Z cross Z as a group has two generators, namely 1, 0 and 0, 1. So 1, 0 should correspond to a particular kind of loop and 0, 1 should correspond to a particular kind of loop, and these are the obvious ones, namely 1, 0 is a loop like this, a loop like this could be, you can label it 1, 0 corresponding to 1, 0, and you can take a loop like this and call this loop as 0, 1, and you can see that or rather what I mean is that you take the equivalence, suppose I call this loop as alpha, and suppose I call this loop as beta, this one, okay. What I mean is that from the fundamental group of the torus to Z cross Z, if you define the map by sending alpha to 1, 0 and beta to 0, 1, of course I should be careful, I should say homotopy equivalence class, okay, and if you want I fix a base point, that can be done, okay. So I can take a base point which is common to which is the intersection of this circle and that circle, so that I have loops based at one point, okay, and then the point is that this map is an isomorphism, okay. So these are all computations that you can look up in any basic book on algebraic topology, and you are invited to justify at least these groups are as they are, as I have written it. These are very basic exercises, you can do that. Okay. So having done this, this is a very brief introduction to the idea of a fundamental group. Okay, and then let me tell you how it continues, how our discussion continues. It continues in the following way. You take topological space X, okay, and what you do is you are trying to look at a space which sits on top of this, which is such that it is like a bundle of fundamental groups of this space based on this space itself. Okay, and that's what gives rise to a covering space. So basically you have the topological space X, okay, capital X, and for every point small x you put a copy of its fundamental group, okay, above, and then you take this disjoint union of all these copies of the fundamental group together, alright, along with the natural projection. The fact is that this fits into a very nice picture, namely the picture of a universal covering space for X. Okay. And of course for this to happen you have to put some conditions on X, and the conditions on X are that X has to be connected, arcwise connected, locally arcwise connected, and also locally simply connected. So if this is true, then this procedure really fits into the picture of a universal covering space for X. Okay. And as I told you, studying these universal covering spaces for Riemann surfaces is what helps you to classify Riemann surfaces. Okay, so I'll stop here.